Alright, time for another draftphysics.com, debatephysics.com also, but debate is impossible, frankly. It's redundant. You can certainly do the redundant part where they just say something. Oh, I don't know. Can't think of any of their stunningly great arguments that they just do over and over and over again. Force isn't energy, something like that. When then what is? How do you put the energy in if it's not going to apply a force? How do you even collect the energy if you're not going to apply it by changing the force? If you're not changing the force, how can you be making more energy? All right. Anyway, so I have working on a page to itemize all of this arguing and reference these videos anyway, the argument videos, and then I'll write up these arguments in some form or another, blah blah. Anyway, so link below, or maybe I'll throw it in the comment section, and to this page that will just give you a brief description of the different argument videos. Okay, so anyway, this is going to be the fifth argument. And, it probably should be the whole 25 times the energy to spin something 5 times as fast. We know that doesn't happen. And I think we know that something spinning 5 times as fast is not going to do 25 times the work. It's just nonsense, silly, and frankly, if you're going to say that for 300 years, you really should be able to show an experiment by now where you demonstrate it. It's so dramatic. Now, on the doubling the energy, this is always, our capacity to see differences, to be able to tell the difference between 30 miles an hour and 40 miles an hour is kind of mushy, okay? Witness testimony sort of sucks. But you can look at something like car crashes, okay? So that has been done. The Mythbusters did it fairly clinically, so, and there was just absolutely no evidence of anything close to kinetic energy being demonstrated. And it was so perfectly almost, you couldn't get much closer to perfect in terms of conserving just the momentum and nothing else. I mean, the 100-mile-an-hour crash creates a car crushed twice as much. And yeah, you can make some excuse like, well, somehow the energy couldn't crush the steel anymore and it couldn't do this. And you can make excuses. I'm just saying, wait, it's just a coincidence that it came out about as perfect for momentum as you could get. So anyway, there's some vagaries. But 5 times, 25 times the fuel, you can't miss that. You can't miss glug, 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 pouring all that gasoline in the car. And you certainly can't miss 25 times the damage. Can't miss it. All right, so anyway, we don't need this. So this argument, instead of doing that, I'm surprised that I haven't put that argument higher up on the list. Let me just say, just because to me, until I see it taking 25 times the fuel to spin a motor 5 times as fast, or I see something going 5 times faster doing 25 times the damage to some normal substance anyway. So we'll get into that, because this really is about how you collect energy, and it's science. So we all should be able to agree that there's so many different substances, so many different kinds of materials, and they're all going to collect energy in different ways. Each one is going to have a vulnerability or a sensitivity. They have skins, they have this, they have that, and all of them are going to absorb energy very differently. I put a pointy arrow, it goes into something's flesh really easy, but if I shoot at a piece of steel, it ain't going to do anything. So it's all about, shapes and velocities that decide how much something penetrates something. And that's sort of gone over with the friction argument and the fact that, friction changes as you change velocity in gravity. You faster you go, the less contact you have with the ground, because the less per inch force is pushing on you. All right, anyway. I mean, it's science, so you have to be able to do some of this thinking in a little bit more dimensions than just this, some sort of flat Earth dimension. You have to actually realize there's variables in the world, and some of those variables matter. All right, so this is just so classic, this water one, so we figure it deserves a video of its own. So I can, have a stream of water, and the simple truth is I can, confine the water to a smaller space, so I can do half the volume. I can cut the volume in half, and I can increase the velocity. So it's 2x the velocity of the water, and I have half as much water, so it's mass and velocity, and I've now doubled its energy. That's the theory. And so the water coming out has twice as much energy. Now I could do that 1 to 3, so I have 9 times as much energy. So that might be a better example. So let's just pretend I've reduced the volume by 1/3, and I have 3x the velocity. Now they're going to tell me I have 9 times the power. So I've taken little water molecules moving, and I've now given them 9 times the power to do work. Now the simple truth is, for hundreds, thousands of years actually, water wheels in one form or another have been used. They've used water to push things and cause them to do work. And you could just argue quite simply that there is no historical record of anyone being able to collect any of that 9, just the one. Can't collect anything more. It can just collect the momentum. So it doesn't matter how fast I shoot the jet. It doesn't matter how much I change the shape of it to try to collect the energy. Never has anyone been able to collect more energy, more power to turn that wheel. So that's why, windmills, and that's why water wheels are always just this big thing, is because they can't really convert it into a small thing and get it to work better. So you could argue that, let's take the wind for example, and I could funnel the wind, make a big wind funnel, and convert, and get, maybe 15 times the kinetic energy in the wind by funneling it, and then shoot that at my little windmill. And I don't have to make a big one now. I can just make a little windmill because I have a smaller stream with, 15 times the energy in it, and then spin my windmill. Does mankind do that? No. There's no such thing as this kind of turbine kind of windmill thingy where you just do this little bit of a gimmick and you increase the turning energy, the force that can be applied to your propeller by any of these bizarre numbers they tell us is there. And there's no explanation for where the energy, this energy is. Why is it so uncollectible? And why in every single case do you always conserve the momentum? That is, come very close. And you never go over. So in none of these experiments can I collect more, even just a little bit more momentum. I can never get even a little bit more. So I have 15 times the kinetic energy, and I can't collect any, not even 1% more momentum. Not even 2%. I mean, they do it. I mean, for they'd probably do it for, 20% increase in momentum. They'd probably construct the thing because all this energy is very valuable. And it just doesn't work, right? So, I mean, I can go to something as simple as just a hose, and I just change the shape of the nozzle, make a smaller and smaller nozzle. The water shoots further. Okay, it sure does that. But can it do more work? And that's the argument. Can it do more work? Now, in some circumstances, like if you want to, abrade a surface or something, yeah, it'll do that better than just throwing a bucket of water at the wall. So you can have the same energy, that is the same number of elemental bits of energy in the sense of mass and velocity. You can have the same momentum with a squirt of high pressure, high velocity water, or a whole bucket of water thrown at the surface. And the two will do different things to that surface. But they're not going to do it because one has more energy. They're going to do it because one is doing something the other one can't deal with. And that's the real argument. So again, this is supposed to be, this is this is a subject for minds that are supposed to be really good at thinking through and measuring and taking in all the details and being careful about how they construct a model. Okay, this is supposed to be science. Okay, and if I have to explain to scientists, okay, that surfaces are complicated, okay, and that the fact is that the surface can be disrupted by different applications of a force. So the most obvious one is yes, I can have a force hit something over a very large area, and we can understand that all the little atoms and molecules will have plenty of time to connect to each other and say, hey, there's a force pushing on us, and they'll spread the force throughout the whole material and keep their integrity. And then if I apply the force over a little tiny area, then these atoms are really going to have a hard time, right? So this is just like if we had a chain of humans. I put a row of humans and they're locking hands. Now, if we apply a force to all of them, all the humans get their share, everybody's okay, 20 pounds of force, no problem. But if I take 2,000, units of force and apply them to one person, so I pick on one guy and I hit him with all the force, everybody knows, the one guy fails, okay, his arms break off, and you have broken the dam, so to speak. So that's even a good example, right? We know it's not more energy because I could drill a little tiny hole into a dam, and over time that little tiny thing, that little tiny effect will tear the whole thing down. So it's all about application. So energy is about how you apply it. And so then we went through in video number 4, I believe, the rolling argument and the whole Galilean fact, okay, that you do this gravity thing, where it's, as you fall, it's 1, 3, 5, 7 in terms of how much increase in distance, but you're always just getting the same 4.9 increase in your actual velocity. The unit of new energy is always just that one little unit. So you just keep adding that free unit to the collected unit, not the free unit, the new unit. And that's all you're doing. Okay, so in the first first fall of gravity, you only go 4.9 meters, and then you go 15 meters in the second unit of time. Why? Well, because you're going 9.8 meters per second. That's the new velocity you have. So the 2 units of 4.9 are free, and you just add one more. And that just keeps happening. All right. And the same thing is with friction. So, all right, so I did you can narrow the surface that you're hitting, okay, and create the illusion of more energy, but it's not actually more energy. And the failure of the system is just that. It's a failure of the fact that the system can't deal with energy in different forms the same way. All right, so you're not using a substance that's going to tell you you're going to be deceived by the fact that there are variables. So all these variables are in the composition of the substance, and you can break it. So I've used the example, you can press on a glass and you're not going to break it, but then you could hit it with a high velocity and shatter it. Even a high velocity sound, theoretically. You can see those experiments where you can see the glass actually moving. So the glass molecules are dealing with it. They're taking the pressure, but there's a certain amount of movement they can't do without not being able to recover. That is, the atoms move too far from each other, and they just stay too far from each other. They can't recombine. So once you tear the crystal apart, the crystal can't just glue itself back together. Just a fact. So again, it's not a complex scientific subject to recognize that it matters how you apply energy. All right, and so velocity matters in the sense that something at a higher velocity is going to have a tendency, all right, to be more disruptive to any surface you can even imagine, because the surface really is just a bunch of individual atoms. The surface isn't titanium. The surface is, it's not some solid thing. It's individual atoms. And it all depends on how well those individual atoms are locked together, how they can deal with a high velocity piece of energy hitting them. So you can understand that, yes, if the velocity is high, it can break the atoms on the surface, and the guys in the back won't even know something happened, because the whole idea of transferring the energy, transferring the pressure between one atom and another atom, breaks down. So the idea of substances is that all the electrons are connected to each other, they feel each other, they spread pressure through each other, okay, and that's how energy moves through an object. And you can defeat that by breaking the atoms right on the surface, and then there's no communication with the rest of the material, and all you do is create a bunch of heat and disruption on the surface. So that's a fact. So that's all there really is. So the hose, okay, I can create this faster and faster laser beam of water, but I'm really not. I don't have any more wattage. It's just like a laser beam argument. Same argument. I can take 5 watts of electricity, and I can put it into a light bulb and spread the photons, or I can put it into a laser beam and confine the photons. I don't have more energy. I have the same wattage going in. I have the same wattage of effective photons coming out. And all I've changed is what surface area I'm going to hit. And if I make it where I've also changed the frequency of the light, that is blue instead of red, I'm also going to have an advantage. But it's not going to have anything to do with more energy. It's just going to have to do with how the surface deals with the energy, how vulnerable it is to the particular kind of energy you're thrown at it. Alright, so sandblaster versus wrecking ball. I can hit you with a certain amount of sand moving a certain velocity, and it won't do anything. I increase the velocity, all of a sudden it starts eroding you into pieces. And the wrecking ball, can hit you, with a pressure, and you can absorb some energy slow enough. But if I increase it fast enough, it just squishes you, and everything, you turn into mush, because it's too much energy too quickly. Your system can't absorb it, it can't spread it, and maybe you just don't even have enough mass to spread it. Okay, I mean, yes, the bullet against an egg or something. So even if you could spread the energy evenly, you'd still cook the egg at minimum, because it's not an insignificant amount of energy. But the fact is, the recoil of the gun can be converted into exactly the same energy, and the theoretical ideal lever demonstrates that it's the same energy, and it's just that we don't have perfect conversion tools. So we can only rely on imperfect ones that only can capture, without waste, a percentage of the energy and do the conversion. So our conversion tools just aren't perfect. We have to pay a price to convert, a small thing going fast into a big thing going slow. We have to pay a price to do that, and vice versa, for a big thing going slow into fast thing going small thing going fast. We just don't have perfect conversion tools, but the conversions are theoretically, okay, there to be had, and it's just the absence of a tool that makes it so we can't do it. We're going to create some heat and some waste. Alright, it's probably enough, but I'll pause and see if I need to add something else. Alright, back. So the takeaway is sort of that you can never use the kinetic energy to do work. That is, you can never turn it into momentum. Momentum does work. Momentum works as a transferable mechanism. You can easily transfer momentum, and you can never, apparently, transfer kinetic energy. You can never convert it bit for bit. So you'll never have there's no experiment where you put the momentum in, you increase the kinetic energy, and then you get a commensurate increase in momentum. All you get is the original momentum, and that's it. In all these experiments, all you can collect is the momentum. So even if I was to concede it's possible that there is something called kinetic energy, if it can't do any physical work, if it can't move a spaceship, and it can't be collected in any device ever, and it can't knock down bowling pins, and it can't do anything that ever converts it into usable motion, how is it energy? Or how is it meaningful? But I'm not conceding its existence, because we know it doesn't have any location. So like Richard Feynman would say, you can't follow it. It doesn't die somewhere where you show what happened to it. It's not in the universe still. Because if you make heat or you make something else, you can see that, you can collect that, you can itemize it, and there's just no evidence it exists, especially in oscillating systems where you would have to create the heat each time the oscillator oscillated. And obviously if you kept making heat as the oscillator was oscillating, the oscillator would lose all its energy. So it's unviable. It always has been, okay, just a notion in somebody's head, and never has it been something clearly demonstrated in the physical world. This isn't physics detecting the truth, discovering the truth. It's physics making a truth up and saying they just like it. Living force. Anyway, just a religion. That's all it is. It's just a dogmatic religion. It's a Holy Ghost. It has no sensible origin, and it has no viability as a theory of reality. I think that's enough.